Okay, we can go with we can do the extra
Well,
math.
it depends on where you put, potential, or, yeah, it depends on where you put potential energy at zero.
Where do you want to put that equal to 0?
At the bottom of 4 meters.
Here?
Yeah.
So this is equal to 0 because Ethan says so. So we cut down on a little bit of the math that we have to do. There will be other times in which we will save a lot more time than in this type problem. All right, so our problem has now been reduced to mgh initial equals 1/2 mv final squared. So we start out with all this potential energy. The way we've defined it, we start out with this potential energy. Kinetic energy is 0, and then as it falls, it gets transferred from one form to the other. So at the end, because of Ethan, it's all kinetic. The mass is irrelevant, mass cancels out. If I want to figure out how fast it's going at the bottom there. So we're left with V final is equal to the square root of 2gh initial. Which is the square root of 2 times Earth 2, so 10 times 4. 8.95. 4 units.
Meters per second.
Thank you. Meters per second. This could have been solved with chapter 2 understanding, but this is just an opening salvo. I'm going to do a very similar problem right now, but it's going to look very different. Any questions before I make it look more complicated? Let's make it look more complicated. I'm going to make one change over here. I'm going to make this 400 meters, which means that's 400, which makes this 89.4. Just, I want the bigger numbers. So now, I've got ground level right there. This distance right here, 400 meters. With the big round head, it's my cousin Robert. Yeah, my wife thought I was joking when I talked about how round his head was. Anyway. Sorry, great memories. He's an idiot. Not because of the head, he's just an idiot. And if you're watching, Robert, you're an idiot. All right, so this is a ski problem here. We will assume that the snow is frictionless. So the coefficients of kinetic and static friction are 0. He's going to ski down the hill, and I want to know how fast is he going when he gets to the bottom. Someone take a shot at it.
V final is 89.4 meters per second.
Hey, how about that? Mathematically, it's the exact same problem. Now, how can we justify that being the exact same problem when that was going straight down and this is not? Well, let's think about the forces involved. When the skier is here, what are the forces acting on him? All right, so we've got weight acting down,
Normal force.
okay? That's it, it's frictionless. All right, so, weight, conservative or non-conservative?
Conservative.
All right, normal force, conservative or non-conservative?
Non-conservative.
All right, so I've got a non-conservative force here, but the question is, how much work is that normal force doing? The normal force is always perpendicular to the surface. As he is traveling in that direction, the normal, so that would be my displacement. The normal force is that way, they are perpendicular to each other. So how much work is the normal force doing?
Zero?
Yeah!
You scare me. I just.
It's just because it looks like I'm never smiling.
Partially.
Okay. Sometimes the obvious answer is correct. Sometimes it's not, you know, you make mistakes. The normal force does no work. So even though there's a normal force here, it's not doing any work because he is not moving in the direction of the normal force. He's moving perpendicular to it. So the only force doing work is conservative work. So that's why it's the exact same problem. If he comes down to the end, he's going 89.4 meters per second. He then goes back up to the top to do it again. This time, there's a cave-in right here. The skier now comes down and he goes, ah. How fast is he going? Right before he hits the bottom.
89.4
Yep, it's the exact same problem. The difference between these three problems is the velocity, but the speed is the same. Because the direction in which he hit, the direction after he's fallen the 400 meters is different in each case. So energy has the nice advantage that you are not dealing with vectors. Unfortunately, it has the disadvantage that you're not dealing with vectors. You ease up on the math, but you now lose some information. Momentum, on the other hand, you don't lose the direction, but you also, the math is not as simple as energy. Questions here?
So if we did, would there be any case where you would get rid of the mass?
All right, so if at the bottom of this hill, they put in a giant spring, now the mass would matter. Because the mass, the bigger the mass, the harder it is to stop it, so the spring, the larger the mass is, the spring would compress more. But that, it's Thursday, so next week we might talk about that, or you'll catch it in the videos, watch the videos. All right, I think on that note, have a really nice weekend.
Hey, when was the last time you showed up?
And
That's
a week from yesterday.